So far, we have seen various concepts related to the flywheels, and we also solved all the previous gate year questions along with some additional questions to understand the depth of the concepts. And here we will discuss one particular example of the flywheels, that is a punching press. So here we use a flywheel in a punching press, and we try to understand and solve how that additional attaching flywheel will affect, not only affect, that's very much important in this punching press. So for example, if I consider a general two-stroke reciprocating engine, so this is my punch that has been attached to the reciprocating engine, and this is rotating like this in this direction, so that this punch, this is a slider, actually this is a slider crank mechanism, simple slider crank mechanism, and this slider is replaced by a punch, and um, this is my plate where I need to get a punch. Sometimes we need to make a hole, that is a punch in the plate, but sometimes we need the blank or the part produced by punch. So it depends on the requirement. So here let's take only punching operation. That means our primary aim is to make a hole in this plate. So this is the simple mechanism, and when this is rotating, this is what we call that crank. When the crank is rotating, this one is making to and fro motion. That is a slider motion. So a reciprocating motion. So when this is moving at this particular instant, this punch is touching this plate, and after the punching operation is completed, the new position of the punch is this one. So it just now completed the punching operation, and its new position is like this, and again it will rotate and make full revolution, and it will go back. So in one cycle, if you observe, in one cycle, the energy required by the engine is only during this period, only for this distance, that is the thickness of the plate. So here only it's a the motor. This crankshaft over here is running by a motor. This crankshaft is connected to a motor, and that motor is providing some power, so that this is making rotations. In turn, this is um, driving the slider. So here the energy utilized or required by the motor is mainly utilized only during this particular period, and the remaining period, this is simply motor is simply providing energy. And if I draw the torque required by the hole to the crankshaft rotation, so here I would like to draw a graph between torque and theta. Here this torque is not engine torque, don't confuse with here. In the previous session we have mainly dealt the torque TT diagram, where T is produced by the fuel burn, but here T is supplied by some motor, and this particular T is torque required to punch the hole. It is not T produced or T given to the crankshaft. For example, let me call T given to the crankshaft is Tm, and and if I consider this as a two-stroke engine, so in a two-stroke engine we have a cycle per 2 pi, sorry, cycle per or crank rotation per 2 pi. So this is a 0. So if you observe, let me draw some angle. So if I consider this as a 0, A and B, so during this position, the angle made by this crank with this reference line is theta. So here let me write that one. So this is the theta one, and in the second position, where if I consider this point as a dash, and this is the b dash. So when the position is O a dash and b dash, theta is, this is the theta, and theta is theta 2. So crank is starting from the 0 degrees, 0 degrees, and it's not doing it, it doesn't require any torque. It doesn't require any torque or resisting torque. For example, if I consider this as a resisting torque or torque required to produce a hole, it doesn't require it's not experiencing any resistant torque until it reaches the angle theta 1. So at the angle theta 1, this punch touches the plate and resisting torque is producing here. So and suddenly it increases, and then it decreases by the time it makes the hole. So this position is theta 2. So from position O A B to O A dash B dash, it, crankshaft is making rotation from theta 1 to theta 2, and energy, this is the energy area under T theta curve is energy, and this is the energy amount of energy that is required to make the hole. This is the energy to require the hole, and that is only from crank rotation theta 1 to the theta 2, and the cycle is completed when crank is reaching 2 pi theta. So let me summarize again. So in this case, this theta is not torque produced by the engine or given to the crankshaft, but rather this is the resisting torque, or let me write it as a TR. So this is the TR, resisting torque. So if I draw a diagram between TR and theta, that is the crank rotation, there is no resisting torque when the crank is rotating from 0 to theta 1, because this punch is moving freely without any resistance, and when the crankshaft reaches angle theta 1, this punch is touching the plate and is trying to punch or pierce to that one. So that means it's starting making hole in that plate, and by the time the crankshaft reaches theta 2, it completes the hole. So again resisting torque becomes 0 when the hole is completed. This is the energy required to make a whole energy, but this energy or power is supplied continuously, power is supplied by the motor that is connected to the crankshaft. For example, if I take Tm or T or simply T, if I consider T as the mean torque provided by the motor, that is the T, and this is the torque produced provided by the motor. So from this diagram, for one complete revolution, energy equal to T, that is the, and if you observe, this motor is continuously providing the torque at a constant rate. So T into 2 pi, this is the energy, but here this should be equal to the resisting torque that is that is required due only from theta 1 to theta 2, from here to here. That means if you chop off area this extra area and you fill this gap, if you fill this gap, then it should exactly fit in this gap. So but here we need extra resisting torque, but motor is providing the continuously this energy. For example, instead of resisting torque, if you forget about this one, and this is the torque produced provided by the motor, that means area is this one, and from that area we have unused energy area. This is the unused energy area, green color, and this is the other unused energy area. This is also green color. So, but here we need extra energy here. So that's why we are attaching a flywheel here. So if you attach flywheel, what happens? That energy, unused energy, this is the surplus energy. This is a surplus energy. Surplus energy here and here would be stored in the flywheel, so that that energy will be utilized during this crank rotation. This crank rotation. So can we say that this energy above the T is delta E, and this delta E stored in the flywheel. So whatever energy above this one is a flywheel. So we will consider now, we will consider some examples, and in that examples our main aim is again to calculate delta E. So how to calculate delta E? So for any problem, we need to identify what is the energy or power supplied by the motor. Here in this particular case, instead of this rotation, if it is stated like this whole process is completed within, for example, 3 seconds, and we know energy of this whole area, this area as the E, then can we calculate power of the motor? Because this whole area, if this whole area is given, if this whole area, if this whole area is given, we know that this is equivalent to this area, this rectangle area. So from here we can calculate energy E, that is equivalent to the energy supplied by the power motor. And if you know energy supplied by the motor, we can calculate power of the motor. Why? Because this cycle is completing within 3 seconds, or whole operation is completed in 3 seconds, that is energy by time. So in that way we can calculate power, and if you know power, we can calculate supplied by the power, or torque supplied by the motor. And if you know torque supplied by the motor and T1 and T2, you can calculate this one. For example, this is the E1. What is the E1? This is actual energy provided by the motor. E1 is the actual energy provided by the motor during the rotation theta 1 to theta 2, and this is the delta E. This delta E is energy supplied by the flywheel. So total energy required by whole E equal to actual energy provided by motor plus energy provided by flywheel. So we need to remember this formula and this formulation, so that we can calculate or we can solve the problem. Here we can derive the some equation in terms of theta 1 and theta 2 and energies, but that is not required. So we try to understand the same concept by solving some problems. So we try to understand the punching process and its concept from this example. So here has given, let's read the example. This is a punching press required to punch 40 diameter holes in a plate of 50 thickness. So this is the plate. This is a plate, and It's a thickness T equal to 15 mm, and we need to make this hole whose diameter D equal to 40 mm. 40 mm, we need to make this much of hole. This is the center, for example, and at the rate of 30 holes per minute. So it's making 30 holes per minute. That means if 30 holes are making in a minute, 30 holes in a minute, 1 minute, how many holes? So how much time each hole is taking? Each hole, how much time? How much time? This is simple multiplication. This one and this one, right? If I consider this as a x, so x into h 30 equal to this 1 into 1, or if you consider this 1 minute equal to 60 minute 60 seconds, so x into 30 equal to 60, this means x equal to 2 seconds. So for each hole 2 seconds are taken. That's what he has given, and it requires 6 Newton meter of or 6 joules of energy per mm square of shear area. For example, once again, let's go back to our original discussion. Here, this is the area. This is the a resisting torque Ts. This is a resisting torque, and this is the crank rotation. For example, this is the crank rotation, and he has given area energy. This whole energy he has given whole energy E, or I will write here. Energy under this area is the energy required to make a hole. So that is given as the 6 new joule per mm square of sheared area. And what is the sheared area? And if you see this one from the top view, this is the diameter of the punch, and the shear area is this is the shear area, this and this is the shear area, and this is like this, and that shear area is around the punch. That would be around the punch, all along the punch. This is the circumference of the punch, and that is up to from top to bottom. So what is the shear area? To D, and it is to the depth of T, so pi dt. So energy is given 6 per shade area, that is the 6 into pi dt. So if you substitute these values, 6 into pi into 40 into 15, no need to convert this one. Why? Because he has given per mm square, so we will keep those diameter and thickness in the mm itself. So it becomes 11309.73 joules. So this much of energy, this whole area is this much of energy required to make a punch. But as you remember, this torque, constant torque, is provided by the motor. This is the constant torque provided by the motor, and this is the area that is energy supplied by the motor. And let's see what else given. And here during this period, this much of energy is only provided by the motor. See, only this much of energy is provided by the motor, and let's say this is the E1, and this is the delta E that is provided by the flywheel. So E is E1 plus delta E. And let's see what else has given. And he has given the whole punching operation, for example, if you take this diagram for one hole, this whole diagram is completed in the, this whole punching operation is from here to here, it's completed in the 2 seconds, right? So 2 seconds. And this area E under this, under this blue curve is equivalent to the area of this one from here to here. That means red color area. So why? Because we already seen that by attaching the flywheel, this excess energy, this is the excess energy is absorbed by the flywheel, that is delta E. And if you choke off this extra energy and fill this gap, that will exactly fit into this curve. So here we know E equal to E1 plus delta E. And if the punching takes only one tenth of the second and RPM of flywheel is from here to here, determine the mass of the flywheel and radius of gyration. So here ultimately we need to find out delta E. So we know formula from delta E, half into I into omega 1 minus omega 2 square. So from this one we need to calculate. So we need delta E. So we need to find out delta E. How to find out? We know already E. If you know E1, then we can find out delta E. What is the E1? E1 is the this green color area. E1 is this green color area, and we don't know theta 1 and theta 2. If we know theta 1 and theta 2, we can multiply by assuming this as a rectangle. We can multiply t into theta 2 minus theta 1. That gives the area of this one. But here instead he has given this whole process would be completed in 0.1 second. And this from here to here, this is the, from here to here, this is the 2 seconds, but this particular punching operation is completed in 0.1 second. So we know E provided by the motor, that is this one. We know this E whole area is equivalent to the this red color area, that is the E provided by the motor. And if you know E, what is the power? Power equal to E by time. That E by time is whole time. E by time for a whole cycle. So power equal to this one, E by 2. And when you know power, we can calculate energy even for this particular time. So what could be the E1? E1 equal to power into 0.1. That means energy supplied by the motor only during the punching operation. This is only during the punching operation. This power is power power given by the motor to the crankshaft. That is a E by 0.1 by 2 into E. So we know E and E1. So what is delta E? Delta E equal to, so if you subtract what, this become E minus E1, then it becomes 1.9 by 2 into E. And if you substitute these values, it it, it comes around 10744.24 Newton meter. So we know delta E, then we can calculate now mass of the flywheel. So half into mass into radius of gyration, k square into omega 1 square. What is the omega 1? 160. 160 square minus this and plus 140 square equal to 10744.24, and k is given as a 1 meter. And if you substitute and simplify, then you get mass of the flywheel equal to 327 kg. So this is how we need to solve this problem. That means if you provide flywheel of this much mass, then only it can absorb all these surplus energy provided by the motor when the punching operation is not taking place or when the punch is idle, so that it can provide the absorbed energy during the punching operation as a delta E. And in this case, we he has given actual punching time, so that's why we could calculate the delta E. For example, instead of giving the actual punching time, if we mention that stroke of the punch, then how to solve? So in the we will consider another example here. If the punch takes 1/10 of the second, so instead, for example, if it is not given, and instead if we given something like a stroke of the punch equal to 50 mm, so this has given, he didn't give this one, so how to calculate? So again, what is the stroke? So if you draw a diagram, this is the plate, and punch is going like this, and this is the maximum limit of the, these are the limits of the punch that can be traveled in any direction. So this has given as the 50, so this is called as a stroke. So when the crank is rotating full rotation in any extreme position, this punch can reach this position, either this position or this position, that is the stroke of this one. And while making a hole, how many times it make stroke, or how many S's it will travel? For example, let's say a punch is traveling from this position A dash, and it reached this position, and now it made a hole and reached this position B dash, and it will once again go back, so it traveled 2 years. So for one hole it's making 2 years, that means how much distance it traveled? 100 mm. Okay, but for one hole, but uh, the actual stroke or actual distance that it needs to travel is only t, that is the equivalent to t. What is the t? But actually is only 15 mm, or resistant torque is applied only during this 15 mm. So here once again we draw the diagram, and this is the resisting torque TR, and this is here, instead of crank rotation, now we will take this punch distance from here. Let's say this punch is traveling in the downward direction as a x, and if you take a punch distance, and this is the area it provided, something like this, and only this this area is only during this t, and this whole cycle is completed in 2 years. So this is the meaning of this one, and this is the area, that is energy. For example, if you consider this as the equivalent of energy, that equivalent of energy is only required during this thickness T, when the punch is traveling only through this thickness, and the remaining time that energy is not utilized. Whole cycle is completed in 2 seconds. So for 2 seconds, uh, for 100 meters, 100 mm stroke, it took 2 seconds. But actual energy is needed only for 15 mm. So that is for how many seconds? In the previous case, he has directly given it's a 0.1 second of the only this actual punching is happening 0.1 second, but here he didn't give. Instead, he has given um, stroke. From the stroke value, we trying to derive the actual punching time. How much we need to know this one. Like same procedure. Consider this as a x, multiply cross multiplication like this, and x into 100 equal to 15 into 2, that is the 30. So 30 by 100, how much? 0.3. So time required, actual time is 0.3 seconds in this case. So we know 0.3 second is the actual time. So again we know E has given energy required by the hole, and what is E1? We can calculate E1 like this. If you can recall from this one, this is the E1. So how to calculate E1? You know E is for whole cycle, and what is the E1? E1 equal to P into 0.3, but P is E by 2. So 0.3 E by 2. And what is delta E? That is E minus E1. That equal to 1.7 by 2 into E. So this value is approximately, what is the value of this one? That is 9613.269. And if you again substitute back in our original equation, then we'll get mass of this one as a 291.31 kg. And in the previous case, how much mass we got? That is in the previous case we got 327, but in this case the mass got reduced. How much? Approximately it's 35, approximately 35 kg reduced. In the previous case, actual punching operation took place for 0. Second only. In this case, the actual punching operation is took place only for 0. Second, but here actual operation is 0.3 second. And if you keep on increase this actual operation, that means this here area is very concentrated, and if you increase the time, for example time of the actual operation, it becomes like this, something like this. And if you further increase, it becomes something like this. And if you, this is the area or energy required for to make a hole, and if you further increase, it becomes like this, and that means it's approaching the actual energy supplied by the motor. I mean, the energy required to make a hole is approaching energy provided by the motor. Why? Because the whole process is distributed instead of concentrating only at one position. So correspondingly, this mass also decreasing. That means if you can make punching operation, or actual punching operation time is equivalent to the full cycle time, then we can avoid using the flywheel. Okay.